Hello, everyone. My name is Yuan. I'm presenting our work today, titled Accelerating Magnetic Particle Imaging with Data Parallelism, a Comparative Study. This is a joint work with my students and colleagues in China while I was in Keio University. Here's what I'll cover today. Firstly, I'll introduce the background of magnetic particle imaging, explain why the NNLS reconstruction is a critical bottleneck, and then I'll discuss our acceleration strategies using two different algorithms on both CPU and GPU. And then I'll introduce the experimental setup and show our results comparing CPU, GPU, and unified memory performance along with accuracy analysis. Finally, I'll summarize our key contributions. So what is magnetic particle imaging or MPI? It is an emerging medical imaging modality directly detects super paramagnetic ion oxide nanoparticles with zero tissue background signal. So this is fundamentally different from CT or MRI. So the key advantages of MPI include no ionizing radiation, unlike CT, and it has high contrast at any depths, has excellent temporal resolution, and also shows real-time imaging potential. So as for a clinical application, because it may allow sub-second reconstruction, then it represents intraoperative guidance, meaning that uh, um, the surgeons can see the imaging results while performing the surgery. So as shown in this workflow diagram on the right-hand side, the reconstruction pipeline takes calibration data and raw MPI signals in, build a system matrix, and then solves a non-negative least square problem to reconstruct the particle concentration image. So here is the problem of the NNLS solver. So it dominates over 90% of the total reconstruction time of MPI for meaningful matrix sizes. So you can see in this chart that as matrix size increases, the NNLS consistently accounts for approximately 90% of computation time. So why is NNLS so expensive? It requires iterative algorithms with dozens to hundreds of iterations. It uses dense matrix vector multiplications with millions of elements, and it has non-negativity constraint projections at each iteration. So the NNLS formulation is also shown here, minimizing the squared error of AX minus B subject to the constraint that X must be non-negative. However, there is also opportunities here. So these dense matrix operations and element-wise projections are highly parallelizable on both CPU and GPU architectures. So this motivates our work on having hardware acceleration for the application. For this particular study, we have tried to accelerate two algorithms. One is active set, the other is gradient projection. So our parallelization strategies are different for these two algorithms. So for the active set method, showing the simplified pseudocode, we parallelize the gradient computation and the set update loop. We use LA-pack on CPU and cuSolver on GPU for QR factorization. For a gradient projection, the algorithm is simpler. Compute the gradient, applied projection, check convergence. So both the gradient computation projection steps are parallel. So the key parallel operations are matrix vector products, which dominate the cost and are handled by BLAS or cuBLAS, and element-wise projection, which is embarrassingly parallel, and also norm computations were parallel tree reduction, and QR solves using cuSolver on GPU and LA-pack on CPU. So our parallelization strategies are different for these two algorithms. So for the active set method, showing the simplified pseudocode, we parallelize the gradient computation and the set update loop. We use LA-pack on CPU and cuSolver on GPU for QR factorization. For a gradient projection, the algorithm is simpler. Compute the gradient, applied projection, check convergence. So both the gradient computation projection steps are parallel. So the key parallel operations are matrix vector products, which dominate the cost and are handled by BLAS or cuBLAS, and element-wise projection, which is embarrassingly parallel, and also norm computations with parallel tree reduction, and QR solves using cuSolver on GPU and LA-pack on CPU. For our evaluations, we have tested the accelerated algorithms on two platforms. One is with a CPU, the other one is based on a GPU. So one thing we should notice is that to enable very large size of symmetrics on GPU, we have to use the unified memory feature provided through CUDA. And also for the GPU, the single precision floating point throughput is 64 times of its double precision floating point throughput. So this is quite common in modern GPUs. Um, as for the results on the CPU side, we can see that this chart shows the speed up with 8 threads compared to the MATLAB baseline. So for single precision, we could achieve up to 60 times speed up. For double precision, we could achieve up to 31 times. So an interesting finding on thread scaling is that 8 threads outperform 32 on the CPU. This is due to the fact that the CPU has P core and E core, so they're heterogeneous in terms of performance. And if we're using less number of threads, we could bind the parallel threads to the performance cores and avoid using something like hyperthreading as well. So this reduces the synchronization overhead and performance imparity. Um, for results on the GPU side, we could see the speed up is quite dramatic. If we try to count the numbers, we could see nearly 1,000 times of speed up on data that are 120 by 120 with this as the system matrix size. And on the other hand, FP64 achieves up to 23 times of speed up. This is definitely limited by the GPU's FP32 throughput. If we try to count the absolute time, we could see a 130 by 130 reconstruction completes in approximately 120 milliseconds, while 81 by 81 takes under 20 milliseconds. And if we have larger data sets exceeding 20 gigabyte VRAM, we could also use unified memory feature. And this enables GPU acceleration for larger system matrix size as 300 by 300. So we could achieve 34 times speed up, having FP32 data. And this is limited by the PCIe bottleneck at 63 gigabytes per second versus the 360 gigabytes per second for VRAM. So we could also see some clinical impact here. So if we could achieve sub 100 milliseconds reconstruction, this will enable real-time intraoperative guidance in surgery. So a critical question then is whether a single precision maintains acceptable accuracy to be used. So this chart here shows the Euclidean distance between FP32 and 64 reconstructions. The maximum error is less than 1% at the largest system metric size. So this error range, um, um, basically speaking, is acceptable, and it grows also sublinearly with metric size remains well under uh, uh, 1% for even the largest system metric size. So it means the running errors are well controlled during the iterative solutions of the mathematical problem. So our conclusion here is FP32 provides clinically acceptable accuracy while enabling dramatic speed up benefits on even consumer GPUs. So finally, the slides covers the conclusion of the whole study. So if you have questions, please feel free to reach me. I'd be happy to answer your questions. Thank you for your attention.